So now we need to consider the concept of the Bronsted-Lowry model. And so this gives us an understanding of how there is a transfer of hydrogen ions in order to show the extent of dissociation of acids and bases. And then this also becomes applied to equilibrium systems. So the learning outcomes for this is recognizing that the relationship between acids and bases in equilibrium systems can be explained using the Bronsted-Lowry model and represented using chemical equations that illustrate the transfer of hydrogen ions, so protons, between conjugate acid-base pairs. We also need to recognize that amphiprotic species can act as Bronsted-Lowry acids and bases. So amphiprotic meaning that it can either act as an acid or a base because it can be a hydrogen donator or a hydrogen acceptor. So for example, like water. Then next we have identify and deduce the formula of the conjugate acid or base of any Bronsted-Lowry base or acid. And then we need to appreciate that buffers are solutions that are conjugated in nature and resist changes in pH when a small amount of an acid or base is added. And so Le Chatelier's principle can be applied to predict how buffer solutions respond to the addition of hydrogen ions and hydroxide ions into the system. So with the Bronsted-Lowry model, we sort of already discussed this when we considered how we have the extent of dissociation of acids and bases and the donation of protons and the accepting of protons. So the basic principle of the Bronsted-Lowry model is that any compound that can donate a proton we will consider to be an acid, whilst any compound that can accept a proton we will consider to be a base. And so an acid can function only as an acid in the presence of a base, and the opposite is also true. So a base can only function as a base in the presence of an acid. And so we also have these concepts of conjugate bases and conjugate acids. So when an acid loses its proton, it becomes what we call a conjugate base. Whilst when a base absorbs a proton, it becomes what we call a conjugate acid. So the conjugate acids and bases only differ from their original acid or base by the difference of one proton. So we have an example here where we're combining hydrochloric acid and ammonia in order to form ammonium ions and chloride ions. So essentially we know that hydrochloric acid is going to be the acid, hence it is the proton donor, whilst ammonia is going to be the base, so it's going to be the proton acceptor. And then when we have this acid losing its proton, it becomes chloride ions, and that is the conjugate base. So when the acid loses its proton, it forms the conjugate base. And then we also have the base, ammonia, gaining a proton from the hydrochloric acid to become ammonium ions, which is the conjugate acid. So essentially we can say that hydrochloric acid is the acid, and hydrochloric acid loses a proton to form chloride ions, which we call the conjugate base. Then we can say that ammonia is the base, but it gains a proton or a hydrogen ion from the hydrochloric acid in order to form the conjugate acid, which is ammonium.